close this door. Okay, well, that's good then. That always makes it nice when you have a little bit of a review. And the reason Ms. McNeil talks with you about photon interactions and matter is because it does pertain to the chances for biological harm. And, we had talked a little bit about that too when we did a little bit of an intro with radiation protection stuff, a couple weeks ago. But photon interactions, the reason I also talk about it at this point is because it does pertain to what our images end up looking like. So it's relevant not only from the protection standpoint and trying to minimize biological effects, but it also comes into play with what ends up producing our images. So that's why, we have to go, into it and make sure that you've got a firm understanding of it, because it does pertain to what our images end up looking like. So we'll talk about coherent, Compton, photoelectric pair production, and photodisintegration. So you did talk about all 5 of these?
Yes.
Okay, so you did hit all 5. Did you spend the most amount of time with coherent, Compton, and photoelectric?
Yeah, we brushed kind of past pair production and photodisintegration, but we talked a lot more about the ones used in diagnostic.
Okay, and that makes sense. And we'll do the same thing. We won't spend a lot of time on pair production and photodisintegration because it's not something that we would experience in diagnostic imaging. Okay, alrighty. So the way I've done these is kind of made these slides here with the key points that you would need to know, the key characteristics about these particular interactions. So with coherent, and I don't know whether you had mentioned this or not, but coherent is also known as, AKA is also known as classical and unmodified. Now, my guess is you probably did mention that coherent and classical mean the same thing. Am I correct? No. What name did you all refer to it as?
Coherent.
Coherent. Okay. Be able to recognize this name, though, because for testing purposes, classical may be used instead of coherent. So make sure that you know classical and coherent are synonymous. It does also happen to be referred to as unmodified, but you don't need to worry about that name. Some of the medical physicist books will still sometimes use this terminology, unmodified. But coherent and classical, make sure you know that. Now, in terms of the types of coherent or classical interaction, did you all distinguish between Thomson and Rayleigh? Okay. Well, if you happen to, and notice it's Thomson, this is not a typo, it's not Thompson, it doesn't have a P in it, it's Thomson and Rayleigh. If you see Thomson and Rayleigh, make sure that you know that it's coherent, it's classical. So basically you have 4 names that you need to be able to recognize: coherent, classical, Thomson, and Rayleigh. When it comes to coherent, there are 2 different types, and it's just because of what is impacted by the X-ray photon. So what we're looking at here, of course, with these interactions is, the X-rays come out of the tube and they head down towards the patient, and these X-rays are going to interact in the patient's body. Well, with coherent, if it's the Thomson type, what that means, and we're not going to go into detail, but what it means is that the X-ray photon will actually cause an electron to vibrate. If it's Rayleigh, then it involves the total atom. So it causes the whole atom to vibrate. So again, we're not going to go into detail because there is more information pertaining to these. The reason I mention it is because for testing purposes, you are expected to know that Thomson, Rayleigh, and classical are all what we call a coherent type of interaction. And here I broke down Thomson and Rayleigh just really more out of interest. I won't ask you this on a test. Not for you all. You don't need to know this amount of detail. But Thomson occurs with photons that have an energy of around 10 keV or less. Rayleigh around 15 keV to 30 keV. Okay. Again, that's not important that you make this distinction here. What is important, though, is that you understand that coherent occurs with low energy photons. And so when I say low energy photons, coherent can occur with photons that have energies of 30 keV or less. Okay, and we do have photons that come out of the tube that have 30 keV photons down to around 10 keV photons. So low energy photons, those are photons basically classified as having an energy around 30 keV or less. Okay, so you with me so far? Okay. When we have low energy photons like this, like 30 keVs or less, this is when X-ray photons exhibit more of a wave-like property. Remember we said that X-rays have a wave-particle duality characteristic? Well, low energy photons, when the X-ray photons are like 30 keVs or less, the X-ray behaves more like a wave when it interacts with matter. Okay, behaves more like a wave. Okay, and we'll see this in just a second. Okay. Now, this type of interaction, coherent, does occur less than 5% in the diagnostic range. So this is not something that occurs very readily inside of the patient's body. Okay? It accounts for less than 5% of the interactions. See, okay so far? Okay. So if you hear the word coherent, what other names do you need to be thinking of?
Classical, Thomson, and Rayleigh.
Right, exactly. Classical, Thomson, and Rayleigh. If you are asked about the photon energy for coherent, what would you say? It's low energy, but if you had to give a number, what would you say?
30 keV or less.
30 keV or less. Okay. All right. So what happens is we have the incident photon. This, in other words, incident photon is just another name for the photon that is entering the patient's body. Okay. So we have that X-ray entering the patient's body. Okay. It's entering the patient's body. And if you notice, it enters an atom in the patient's body, and then it ends up changing direction. And anytime we have a photon that changes direction, it's referred to as a scattered photon. But what do you notice about this scattered photon? Look at the wavelength and the frequency, and compare it to the wavelength of the frequency that it had when it entered. Is there any change in that wavelength and frequency, or is it the same?
Seems to not have lost much energy.
It doesn't lose anything. It's identical. Okay. So in this situation with a coherent interaction, the photon comes in and it just simply causes either the electron or the atom to vibrate. Okay. And then it ends up changing direction and leaving the atom. Okay. So essentially what's happening is the photon energy is kind of getting absorbed. It's getting absorbed when it causes the vibration. That atom, for example, is taking on that energy, and then as it vibrates, it re-releases that energy, but it has the same frequency and the same wavelength. All that basically happens is that the atom heats up a little bit. So when the photon comes in, that photon energy essentially changes into heat, the atom vibrates, and then that energy is re-released as a scattered photon. But there is no change in frequency or wavelength. Low energy photons, we talked about this when we looked at the electromagnetic spectrum. And, when we talk about the electromagnetic spectrum and the low energy photons, for example, like radio waves and microwaves, we said that those photons don't have enough energy to ionize atoms. Remember when we talked about that? But that they could cause atoms to heat up. This is how an X-ray behaves, like a wave. Because like the electromagnetic spectrum, the energies that are at the low end of the spectrum, they have wave-like properties. They behave like a wave. They heat atoms up, but they don't ionize atoms. It's not until you get up around ultraviolet and X-rays and gamma rays that there's enough energy for the X-rays to actually ionize an atom. Okay. So the coherent interaction is a type of wave-like interaction. So the atom, will have some heat generated in it, and then when the scattered photon is released, there is no change whatsoever in the frequency or the wavelength. So we know an ionization has not occurred. So this is where the photon acts like a wave. Does that make sense? Make sense to you? So for the patient, no ionizations have happened because we do not have any electrons being knocked out of orbit. We simply just have a little bit of heat being generated. Okay? In terms of image quality, there is a negligible impact. This scattered photon, chances are it is not going to make it out of the patient's body and reach the image receptor. So it's really not going to have an impact on degrading the image. Okay. So you okay with that one? Okay. So that's your coherent. That's your coherent. Compton, this is a biggie. Okay, and you talked about Compton. Compton, some other names it's referred to as is non-classical or modified. Do not worry about these names. I just put this up here just kind of out of interest. I will not ask you these names on test or on a quiz. Okay, so for testing purposes, don't worry about this. Now, Compton, it occurs with what we classify as intermediate energy photons, which is it can be classified as equal to or greater than 15 keVs. Now, you might be saying, well, why isn't it greater than 30 keVs? Intermediate is if we end up with a Compton interaction occurring at 15 keV, it's classified as intermediate because Compton does have enough energy to knock an electron out of orbit. Whereas with a classical interaction, it is possible that we can have some 30 keV photons that do not cause ionizations. And if the atom is not ionized, it is classified as a coherent interaction. So I don't want you to get confused by that, okay? So with Compton, it does occur with intermediate energy photons, meaning that at 15 keV or greater, there is a chance that an electron could be knocked out of orbit. And if it's knocked out of orbit, it's a Compton interaction, okay? It occurs with outer shell electrons. And the reason it occurs with outer shell electrons is because they're loosely bound. You know, we had talked about loosely bound outer shell electrons just don't have a lot of binding energy to hold them in place. And because Compton does occur with outer shell electrons, it is the most common interaction that does take place in the human body. Okay? So atoms have loosely bound outer shell electrons, and we have a very, very high water content in the body. Now, when you look at water content, what is water composed of? What molecule is water?
H2O.
Hydrogen and oxygen.
Hydrogen and oxygen, right? H2O. Hydrogen, what do we know about hydrogen? In other words, where does it fall on the periodic table? I mentioned this to you a couple weeks ago. What is its atomic number?
1?
Is it 1 or 2?
1. Right. It's 1. Okay. Since it's number 1, what does that tell us about the electron binding energy? Because what did we say about atomic number and electron binding energies? What's the relationship?
So the lower the atomic number, the lower the binding energy?
Exactly. So hydrogen, that electron hardly has any energy holding it in place. And since our bodies are mainly composed of water, around 80% or so of water, that high water content, we have a lot of loosely bound outer shell electrons in those hydrogen atoms. So it is very, very easy for photons to knock those electrons out of orbit. So that's why Compton is the most common interaction that takes place in the human body. Okay. So this is what it looks like. This is what's happening here. So we have a photon that comes in. It knocks an outer shell electron out of orbit. And by the way, the name that is given to the electron that's knocked out of orbit is referred to as a recoil electron. I don't know if you all mentioned that in your class with Miss McNeil or not, but you do need to know that a recoil electron, it's just simply the name given to that electron that has been knocked out of orbit, okay, knocked out of its shell. Then what do you notice about the incident photon? Is there a change in direction?
Yes.
From the way it came in? Yeah, because here's its direction initially. There's a change in direction. And what else do you notice about it?
Changes energy.
Change in frequency?
There's a change in frequency. Why is there a change in frequency here?
Because it gave up energy?
Gave up energy. Remember, there's a relationship between frequency and energy, right? There's a relationship, a direct relationship. So if energy is given up, then the frequency is going to end up decreasing. So we've got an increase in wavelength, a decrease in the frequency because energy was given up. Where was that energy given up?
The binding energy when it gave up or when it knocked the electron out of its shell.
Right, when it knocked that electron out of its shell. So energy was given up. Okay. But if you notice, there still is a relatively high frequency for this photon. In other words, it's not going to give up a whole lot of energy. The reason the photon doesn't give up a whole lot of energy is because the outer shell electrons are so loosely bound. It does not give up a lot of energy. Okay? Well, in terms of the patient, there's a potential for biological damage because an electron is missing. Okay, and that's the type of stuff that you're talking about in radiation protection is the biological harm that can occur. We just talked briefly about it, and I'm sure you're going into more detail with Ms. McNeil. In terms of the radiographer or the technologist, there's a potential for biological damage to occur. Now, again, remember, we're pretending that this is an atom inside the patient's body. So how in the world can there be a potential for harm to us? Why?
Because it can mess with our electrons in our bodies.
I'm sorry, I couldn't quite hear.
I said it could probably mess up the electrons in our body.
Okay, and how can it do that? Because this is in the patient's body. But you're right.
It could knock out an electron, or
it can knock out an electron in our body. How in the world is that possible? If that X-ray beam is aimed at the patient, how do we end up being impacted? Well, the scattered photon, it does not lose a lot of its energy because this electron is so loosely bound. So this photon will still retain quite a bit of energy. For example, maybe there's a procedure being done and the KVP that's being used is 120 KVP. So that means we have photons exiting the tube that have 120 keVs worth of energy. Well, maybe only a couple keVs of energy is given up to knock this electron out of orbit. So this photon may still have a good 118 keVs worth of energy. So there's a chance that that photon will exit the patient's body. And if we're doing like a fluoro procedure and we're standing there next to the table where the patient is, if that X-ray photon exits out the side of the patient's body, it can end up entering our body if we don't have the protective apron on. So the Compton scattered photons are very energetic, very energetic. Okay, some make it to the image receptor, but some make it out of the patient and can end up interacting with us. And that's why we talk about time, distance, and shielding. Okay. In terms of image quality, like I said, some of these photons will actually make it to the image receptor, and it will decrease the quality of our image in two areas. It will lower the contrast. We'll be talking more about this, but it will lower the contrast. In other words, it makes the images gray, but it's useless gray. It doesn't have any information. Okay, it's like fog outside. You know, when it's foggy, that's useless information. It makes it very hard to see things. So it lowers the contrast, and it also will reduce our visibility of image sharpness or spatial resolution. And we'll be, talking more about this, but to kind of give you an idea, if it's a foggy day, fog is, it's very gray and it's useless. Well, what if there's a speed limit sign there? And speed limit signs are high resolution, very high resolution. It's a black and white sign, very sharp letters, very sharp, printed numbers. But if it's foggy out, could that impact your visibility of that sign?
Yes.
So you don't see the details of that sign because it's foggy. And that's what scatter radiation is. It's useless information. It could hide things that are significant that, the radiologist needs to see. Maybe that scatter is hiding a fracture. It's covering it up. It's just useless gray. So that's why we don't like the Compton interactions. Okay. You okay so far with Compton? Okay. All right. Now, I didn't draw the whole atom here, all right? But you have to pretend that this, we've got a whole atom here in the patient's body, but I'm focusing on that outer shell electron because I want to show you a couple things. X-ray photons that have higher energies to begin with have what we call smaller scatter angles. So the more energy an incident photon has coming in, the more likely it is to make it to the image receptor. Okay, so we're pretending, this is the X-ray tube here, and we've got a photon that is entering into the patient. And if you notice, when it knocked that electron out of orbit, that's our recoil electron, the incident photon, it did give up a little bit of its energy, because you can see there's a little change here in the wavelength and the frequency. But notice that it basically continues to the image receptor. Its angle only deviated a little bit from the straight path. Okay, so there's only a slight change in the angle of this X-ray beam, and it's going to make it to the image receptor, and it's going to add useless information. Now, if we have an X-ray photon that has lower energy that exits the tube, and it knocks an electron out of orbit, because it's lower energy to begin with, what happens is we end up with a larger angle, a larger photon scatter angle. See, this is a bigger scatter angle than the scatter angle here. So higher energy photons have what we call a small scatter angle. Small scatter angle, meaning they are more likely to keep that forward direction towards the image receptor. Whereas this photon here that has lower energy it has a larger scatter angle, meaning that photon is more likely to miss the image receptor. Matter of fact, that photon might actually come out of the side of the patient. So it doesn't continue that straight path down towards the image receptor. Does that make sense? Okay. Now, just to show you, though, you don't have to memorize this. This is just so, to help your understanding here of how much energy photons can retain. We're pretending we have a photon that has 70 keVs worth of energy. Okay, so that means we were at 70 keVp. I've got photons that have 70 keVs worth of energy. We're pretending this is our max energy here. Well, let's pretend that the 70 keV photon only has a scatter angle of about 20 degrees. Has a small angle scatter. Look how much energy it retains. So if it's only scattered 20 degrees, it's going to retain a bulk of its energy. And there's a good chance that's going to make it right to the image receptor. But look what happens as the scatter angle increases. As the scatter angle increases, what happens? And it is possible that a 70 keV photon can scatter these different angles here. Okay, it is possible.
Just the energies go down as the scatter angle increases.
Right, it tends to lose more energy as that scatter angle increases. Okay. Small angle scatter refers to any photon that has a scatter angle less than 90 degrees. In other words, if it scatters less than 90 degrees, then there's a high probability it is going to make it to the image receptor. So with this example here, what would be considered small angle scatter? Just with this example here, what two scatter angles?
60 and 20.
60 and 20, okay, 60 and 20. So small angle scatter is anything that has an angle less than 90 degrees, because that means it's going to make it to the receptor, okay? Once we get a scatter angle of 180 degrees, it's referred to as backscatter. What does backscatter mean? What is that incident photon doing? It interacts with an electron. We have a change in direction. So now what does that scatter photon do in terms of its direction? If it's called backscatter, what direction is it taking?
It's going backwards.
It's going backwards. It's going back the same direction that it came in. So you can have, if a patient is lying, if they're AP on the table, so the chest is facing the tube, the x-rays come in and they interact, but then the scatter x-rays will exit back out the front of the patient. That's what backscatter is. So they scatter back in the direction that they came in. But the interesting thing, and to show you the impact of Compton, is even at 180 degrees, the photon still retains approximately 2/3 of its energy. So, approximately 46 keV is about 2/3 of 70 keV. So that's the power of Compton. It retains a lot of its energy. So that's why when you're doing a fluoro procedure, there are a lot of photons that do end up exiting the side of the patient, and they're very energetic. And that's why you have to wear an apron, because there's enough energy for those photons to get into your body and cause ionizations. So they're very energetic. So on a test, if you were asked, what does small angle scatter mean? What would be a good answer?
The angle is less than 90.
Any angle less than 90 degrees.
Any angle less than 90 degrees, which means that there is a very strong likelihood that photon will do what? Where will it go?
To the IR and continue on with like 90+% of its original energy.
Yeah, it'll continue on to that image receptor. So there's a very high probability that small angle scatter will make it to the image receptor. Is that useful information? Scatter is always bad information, okay? It's useless information, okay? Useless information. So you okay up to this point?
Mm-hmm.
Okay. Why don't you all go ahead and let's take 15 minutes to come back like at